also referred to as energy levels, because it takes a specific amount of energy to get to that level. When the electron checks in, it is assigned the first level. This is the electron's normal or resting energy level, what scientists call the ground state. To move the electron between the ground state and higher energy levels, the atom must absorb energy either through collisions with other atoms or by absorbing the energy of a photon of light. An atom that has absorbed energy in this way is said to be an excited atom. The Doppler effect is the apparent change in wavelength of a wave depending on the motion of the source toward or away from an observer. Astronomers observe this effect with wavelengths of light, but we experience it with sound as well.
If you've ever stood there on a street corner and you've heard an ambulance go by, first thing you hear is a very high-pitched noise, as it's say coming from your left and passing by you. And as it passes by you, what you hear are lower frequencies, a very low-pitched sound. So what is happening in that instance is, as the ambulance is coming toward you, the sound waves that are getting transmitted by the horn on the ambulance, the sound waves are compressed. As it goes away from you, those sound fronts, you could say, get stretched out. So it corresponds to a longer wavelength and a lower pitch. So you hear a lower sound. The same principle can be applied to light. If you have something coming towards you, you will see it, the spectrum get shifted but towards shorter wavelengths, and those shorter wavelengths are mainly blue wavelengths. So it gets shifted, they say, toward the blue. If something, and this happens often in astronomy, if something is going away from you, it's going to get shifted toward longer wavelengths, and that's mostly toward the red.
These shifts are classified by the direction they move within the spectrum. Objects moving away from us exhibit shifts to the longer wavelengths. We call them redshifts. Objects moving toward us exhibit shifts to the shorter wavelengths and are called blue shifts. The third type of spectrum identified by Kirchhoff is the absorption or dark line spectrum. This occurs when a cold gas is between an observer and a source of continuous light. The gas absorbs the light that has the correct energies to boost its electrons to its various energy levels. All other light passes through. By the time the light gets to the observer, those energies absorbed by the cold gas have been removed and appear as gaps in the spectrum. Instead of bright emission lines at specific energies, absorption spectra show dark lines where energy is being absorbed by the atoms. Stars produce absorption spectra. The surface of a star is cooler and thinner than the gas underneath. The light from the hot, dense gas inside a star will produce a continuous spectrum, and the cooler gas above it will absorb specific wavelengths of that light, which appear as gaps. Kirchhoff's first law deals with the continuous spectrum. As opposed to emission spectra, which appear as bright lines at specific wavelengths, continuous spectra are produced by an object that gives off light at all wavelengths. For example, a horseshoe is being heated in a forge. As it heats up, it changes from dull red to brighter orange to brilliant yellow light as the atoms become more excited, causing more collisions and radiating photons at shorter wavelengths. So the hotter the object is, the brighter it becomes, and the higher energy photons it will emit. But it also radiates photons at all the other wavelengths because the atoms are so crowded and interact so forcefully that they produce light of every color. Each atom wants to give off light at its own specific energy, but the energy levels are blurred. A solid, liquid, or dense gas excited to emit light will radiate at all wavelengths in this way and thus produce a continuous spectrum. The peak or brightest color of the spectrum indicates the temperature of the object. The value of the continuous spectrum to astronomers is that it easily reveals an approximate temperature of a dense gas. However, unlike the emission line spectrum, it does not reveal the composition of that gas. In the mid-18th century, a German scientist named Gustav Kirchhoff identified 3 different types of spectra through experiments as he burned chemicals in his laboratory and observed the light they emitted. His classification now bears his name as Kirchhoff's laws. The 3 types of spectra Kirchhoff observed are called continuous spectra, emission or bright line spectra, and absorption or dark line spectra. The easiest to understand is actually Kirchhoff's second law, the emission spectrum. This deals with the absorption of radiation by electrons in a low-pressure gas, which re-emits that radiation at different wavelengths. An emission spectrum is observed as bright lines in the spectrum. These are caused by the electrons emitting photons at specific wavelengths as they move toward the ground state from higher energy levels. The Babcock model explains the magnetic cycle as a progressive tangling of the solar magnetic field created by the differential rotation of the sun, the fact that it's rotating much faster at the equator than at the poles. Because the sun's ionized gas is a very good conductor of electricity, it takes the shape of any magnetic fields that are present, and the fields are thus frozen into the gas. So when convection or rotation moves the gas, the magnetic field moves with it. Thus, the differential rotation wraps the field around the sun like a string on a spinning ball. Where these magnetic strings burst through the sun's surface, sunspots appear. The result of this magnetic activity can also be seen as solar flares, massive eruptions on the sun's surface. The most obvious examples of solar activity include sunspots, the darker patches that appear regularly on the surface of the sun. The Chinese made the first recorded observations of sunspots as early as 800 BC. These observations were probably made during periods of dense fog or at sunset when the sun can be safely glimpsed with the naked eye. In 1609, Galileo made the first telescopic observations of sunspots.